Hello again, Dave here, and today I'd like to talk to you about power. My last video we talked about energy and work, and we talked about energy being the quantity that we measure in terms of joules for the ability to do work, and work we talked about being simply a push or a pull across some distance to some object, generally speaking. We can also use energy to do work in terms of heating something up, and this is kind of the direction I'm going to take. Today's topic is we're going to talk about the rate at which that work is done, and the rate at which work is done is called power. So today, my pen working here, power. So when we take energy that's stored in one form and we convert it to energy in another form, the operation or the process in between is the work. And so we're going to convert energy from one form to another, and how quickly we do that is going to determine how much power is involved. So for example, I've got a barbell here, 1 kilogram, and if you think about me lifting this up slowly, I'm not using a lot of power. I'm doing the same amount of work if I cover the same distance, but I'm not using a lot of power. If I lift this a lot faster, that's going to be I'm using more power to do it. Let's give you an equation here. So we're going to say that power is equal to work divided by time. And we're going to measure work. My screen over me. Or energy in joules, and we're going to divide this by seconds. And we have a different unit for power, that is the watt. So 1 watt equals 1 joule in 1 second. So if I accomplish 1 joule of work, that's about equivalent to me if I lift this apple 1 meter, or about a yard, a little more than a yard, this is 100 grams roughly, or a quarter pound. So if I lift a quarter pound apple about a yard, lift a 100 gram apple about a meter, the amount of work I've done from resting point to raise this up is 1 joule. And if I'm picking apples up off the ground and putting them in a basket that's a meter up off, or on a table or something, if I lift 1 apple every second, I'm accomplishing 1 watt of work. I might have my numbers backwards there. Sorry. No, I'm correct. Likewise, if I lift this is about 10 times heavier, so if I cover a tenth of the distance, about 10 centimeters or 4 inches, if I lift this weight 4 inches, I've accomplished the same amount of work. And if I do this once every second, I'm accomplishing 1 watt of energy, just to put things in perspective. Likewise, I have a little light bulb here. And this light bulb is, my camera, angle this for the camera here. So a regular incandescent light bulb. This one happens to be 40 watts, listed right on the top there. So every second that this is on, this is going to take 40 joules of energy from the wall, or from wherever it's plugged into, and turn that into a combination of forms of energy, namely light and heat. Not much else. Light and heat, that's all this produces. When we talk about energy efficient light bulbs, the general idea here is we change the technology inside, so we get more light, less heat. It's the general idea. And typically we can get more light for less watts, or we get the same amount of brightness using less watts of electricity, fewer watts of electricity. So some of these light bulbs have a second pin on here, and you can buy tri-lights. So a tri-light draw the base of the light bulb and draw the bulb. There are actually two filaments inside a tri-light. There's one, and there's another. So one of these, when you turn on one filament, it gives you 50 watts of light and heat. And when you turn on the other one, the little rotary switch, it'll go click, click, click. There'll be 4 different positions. One is off. First position would be 50 watts, so you get like a dim glow. And then the second position, we turn on the other filament instead, we get a medium glow. And then when we combine both together, we turn them both on, we get 150 watts. So that gives you maximum brightness for that particular bulb. So these are typically found in a living room. Let's go on to our next slide here. So I'd like to give you a few more examples of what of power. For example, I happen to have a wireless router here for my internet, so let's aim my camera down. Got a few things here on my table to show you. This is my internet hub. So I've got cables in the back. One goes to my printer, one goes to my modem, one goes to a scanner, goes to a few different things, but I also have an antenna on here, and I've also got lights, blinking lights, and if you put your hand on there, you'll notice it's a little bit warm. Not uncomfortable, but it does produce a little bit of heat in the process of the circuitry inside, making all the decisions they do about whether or not my neighbors are attempting some sort of password crack or not. It's going to do some processing, and the brains inside the chip is going to use some of that energy to operate. Let's look at how much power this has. So this is a slightly different example, and without getting too technical, I might do this as an aside in perhaps another video, but I can read the label right from the bottom. Did this earlier today. And it gives me 9 volts, or the power supply it needs is 9 volts, and it, worst case scenario, when it's working as hard as it possibly can, which isn't necessarily all the time, it needs at least 0.85 amperes. And the cool thing about the metric system is we can simply multiply our volts times our amps to get our power. So if I multiply 9 volts times 0.85 amps, I get 7.65 watts of energy. Watts of power, I should say. So where does this 7.65 watts go? Some is heat. Some of this goes to operate the lights on the front panel. Some of this goes down the cables at the back to send electrical signals to my printer and other devices. And some of this energy is broadcast through an antenna. Let's look at a few other examples of power. I'm going to come back to this one, I think, and compare it later, but another thing we can do is we can heat up water using power. So here I've got a measuring cup, plastic measuring cup with 250 milliliters of water. Weighs about 200, or has a mass of 250 grams approximately. And I'd like to show you the calculation for how we would figure out, let's assume this is at room temperature of 20 degrees, and we want to bring it to boiling. 20 degrees water. 250 150 grams or quarter kilogram. And we want to bring it to 100 degrees. I should put Celsius there for any American friends who are watching. This would be 68 Fahrenheit to 212 Fahrenheit, I think. So we want to raise the temperature of this water using electricity from room temperature 20 or 68 up to 212 or 100 Celsius. I'm going to talk about 3 ways we can do this, and then we'll compare how much power we use to do that with our wireless router. So first of all, I don't have it with me, but in my kitchen is a 700 watt microwave oven. So now what we could do now is if we know how many joules of energy we need to raise the temperature, and we know how many joules per second our appliance delivers, or how many watts, we can then calculate how much time it should take. So the way we do that is if you know the material, there's a certain number of joules required for every kilogram for every degree Celsius. 4,200 is the number for liquid water. If you're trying to cook something else, don't quote me on this because you're going to have to change the equation for whatever other material you're using. But generally, anything that's predominantly water, you can use this number. So let's find out how much power, or how much energy I should say, it's going to take. So let's multiply by our quarter kilogram, and we'll multiply by going from 20 to 100 Celsius would be 80 degrees. So 4,200 joules per kilogram per degree Celsius multiplied by the quarter kilogram multiplied by the 80 degrees rise in temperature. Extend my page here. 84 kilojoules required. Let's look at our 3 different appliances then. So if we've got 84 kilojoules and we divide by the power of my microwave, 700 watts, and that's the same as saying joules per second, I get 84,000 divided by 700, 120, that's not degrees, that's seconds, 120 seconds, or 2 minutes. And from practical experience, that's about right. I could put this in the microwave for 2 minutes and it would be close to boiling, or just at the point, just before boiling. It takes more energy, and there's a different number we use to convert from 100 temperature water to 100 temperature steam, but that's another story. So 2 minutes would bring this to just about boiling. I've got a small burner from my stove. I'll stand so you can see this. These just slide in and out. And for those of you that have not taken these out and explored them, don't do this when they're hot, but there's numbers printed or stamped onto the edge here. And this says 240 volts, 1250 watts. So let's repeat our calculation. Use a different color ink here. Small, we'll call this a range element. So it takes the same amount of energy to bring the water up to the same point, but this time we're going to divide by more power, 1250 watts. So 84K divided by 1250 equals 67.2 seconds. And I think you could have well imagined that 700 watts microwave and a 1250 watt stove element, this is almost double. This is almost 1400. So this guy is going to heat my water up almost twice as fast as my microwave. Now to be done, I've got the larger burner here. Let's pick another color for the large guy. This one is large, 2400 watts. So 84 kilojoules divided by 2400 watts equals 35 seconds. So we can use my microwave, 2 minutes to warm this up. Stand so you can see it. If we use the small stovetop element, 67 seconds. And if we use the large element on maximum, I should say, use these all on max, it takes us 35 seconds. Let's entertain a hypothetical question here. And I'm going to draw your attention back to my wireless router. Remember we said this puts out, or it draws 7 watts from the wall? Let's do the calculation, and hypothetically, if we could cook water or heat water with this appliance, let's see how long that would take. 80, oops. I'm going to take my 84 kilojoules required to raise the water temperature, and I'm going to divide by 7.65 watts. 84,000 divided by 7.65 equals 10,980 seconds. Let's divide that by 60 to get our minutes. 183 minutes. And let's divide that by 60 again to get hours. 3.05 hours. So, the lesson here is, the point I'm trying to make, I can use a large element and I can heat this water up to boiling in 35 seconds. Use a small element, heat the water up in about 67 seconds. I can use a microwave and it'll take me 2 minutes. Or, if it was possible, maximum, if instead of, well, we'll talk about where the power is going here, but if I could take all the power that's coming through this power cable and put it all straight into the water, it would take 3 hours to raise the temperature of the water up to boiling. Now, of course, air currents and room temperature and everything else are going to get in the way. Some of the power is, not all of that 7 watts is coming out of the antenna. Some of it's coming out of the lights. Some of it's actually the warmth from the processor inside, thinking about all the calculations it needs to make sure signals go to the right place. So we've got lights, we've got heat, and then we've got the antenna. This leads into my next topic and next video, in which I'm going to talk about power density. So if you imagine this was a can of spray paint, and I sprayed, instead of using electricity, I used paint, and I sprayed a sheet with paint instead of power, if I have the sheet really close by, it's going to get a lot of paint. If I hold the sheet much farther away and spray the paint onto the paper, it's going to pick up much less paint. So I would have to direct all 700 or 7 watts. 700 was my microwave. It's going to take 100 times longer than the microwave. If I could direct all the power directly into the water, I could still heat it up in 3 hours. But the fact of the matter is, the energy is dispersing in every which direction, and so it's going to take much longer than 3 hours simply by virtue of the distance and the scattering or spreading effect. So standing at this distance, yes, there is some warmth. There's probably more warmth coming off the cabinet itself than is coming from the antenna. Actually, that's cold to the touch. This is slightly warm. So that's the long and short story about power. Hope you found this educational at least, and possibly entertaining. But that's it for today. And next video, I'll talk a little bit more about power density. And that's once we've covered power density, that's one piece of the 2 pieces to the puzzle regarding Health Canada's Safety Code 6. So that's my goal, is to get us to the point where we can look at Safety Code 6 and understand power density and frequency and what roles they play in cellular, telephone, and health. So that said, I'll sign off for today. Thanks for watching.